Right, good morning, good afternoon, good evening. Welcome back. So I hope you had a chance to view the videos on normal distribution. They're really good quality and they cover a lot of the basics that you'll need to know. But I wanted to just share with you some actual problems that we'll do. And also just add on to what was introduced in the videos. The questions on the first video at the end are maybe a little bit below our level. So they're the kind of questions I might ask you right in the middle of a lecture. They're good for your understanding, but they're not the kind of thing I'm going to be testing you on. The question at the very end of the second video, when they were actually using the z-score to calculate probabilities, that's basically the most basic level questions I'll ask you. So in this video, in this lecture, I wanted to cover some of the problems and questions you'll see that go beyond that. Well, we'll do that as well, and some of the ways to do it. I also want to show you some technology using Desmos to find z-scores or probabilities from z-scores in another fashion. All right, let's just start off with some quick notes on the differences from the video and from what I'm going to expect you guys to know. So first of all, this is a minor detail, but I just wanted to mention it. So on the video, he says standard deviation S is our statistic, and for us, we've been calling it sigma x bar. Okay, so that's our standard deviation of a statistic. Small detail that was on the first video, but I do want to point that out because we haven't used the S. Another detail, so the way that you write the normal distribution in our familiar notation like this is to put the mean, and now your textbook has the variance here. They put the variance here, and I've seen that in other textbooks. I think a lot of older textbooks and more advanced textbooks usually have the standard deviation here. I mean, not the standard, they have the variance, but for our purposes on Desmos and just in general, I prefer this standard deviation, and you'll see why as the more we use these and calculate probabilities from these. The standard deviation is what matters, not the variance. Okay, and there is a PDF, a probability density function, and just for continuity, I'm going to show it to you just for continuity with the previous video and the previous discussion on continuous variables. So here it is. So 1 over sigma square root of 2 pi e to the negative x minus mu squared over 2 sigma squared. Okay. There it is. There's the monster. That is the PDF. That's basically the function that gives you that nice smooth curved graph like this. Okay, so that's what the graph of this f looks like. And the mean is the highest point here. Oh, it's always the highest point on this graph. And when we're calculating probabilities, we're still going to have the same. What we're calculating is still the probability that x will be in a certain interval, and it'll still be the integral of a function, in this case, this nasty thing. So it's so big I don't even want to put it in here, but I'm referring to this. We're still doing this, but the great thing about the normal curve and about these kinds of distributions is that they all have similar properties based entirely on their standard deviation. So we don't have to do all this complicated calculus. There's a lot of shortcuts, and the main shortcut is the one you saw in the second video, where you basically transform every value you have into a z-score, or basically you're rescaling your curve into the standard one, which is centered, which has a mean of 0 and a standard deviation of 1. So basically when you're calculating a z-score, you're only calculating how many standard deviations you are from the mean. All right, here we go. Here's a kind of problem you might see on your homework or on an exam in the future. We have the weights of female cats of a certain breed, and they're normally distributed, and we have the mean is 41 kilograms, and the standard deviation is 0.6 kilograms. So we just take down that information right away. We have a mean of 4.1. We have a standard deviation 0.6. And look, before we usually would write out this notation here, for the normal curve, there's an exception. You don't really have to write this out. This is not common to actually write this out as a distribution because we just go straight to using the z-scores. Okay, so what proportion of female cats have weights between 3.7 and 4.4? So what that's asking is if we have the curve here. Oops, sorry, it's a little tilted here. The curve here has a mean of 4.1. And we're asking the area between 3.7, so this is just a sketch here, and 4.4. We're asking for the area under here. Okay, so let's go to Desmos and see what that looks like. And the way we can do this is type in x equals normal dist, and notice the font changes, and now we can type in our mean and standard deviation. So for this question here, we had a 4.1 and a 0.6 standard deviation. A nice little feature here on Desmos is you can click the zoom to fit, and it'll center your graph for you. So here's our curve describing the probabilities here. And if you want to calculate the probabilities, we can click this find cumulative probability distribution, and this is giving us our bounds. This is giving us our little a and b, and it asked us the question. Let's look at the question real quick. Okay, it wants the weights between 3.7 and 4.4. So 3.7 and 4.4. Okay, so the area under here, that is written right here, 4.389, or we can round it up to 0.44, and that's our percentage. That's our probability. That's our probability that any cat's weight is going to be between 3.7 and 4.4. So I'll come over here and I'll answer that. This question, the answer was 0.4. So, okay, so we have 0.44, or 44% of our cats have a weight between 3.7 and 4.4. So notice I did this in a different way than calculating the z-score. I skipped that step. So I want to go back and do this another way, a common way, which you should have seen on the video, and which is instead of doing this directly from this specific distribution, what I'm going to do is use the standard distribution. So the standard distribution always has a mean of 0 and standard deviation of 1. And I've changed the bounds here to be negative infinity up to z. Okay, so z is the same variable, your z-score. And I'll add a little slider here, and I can change the bounds here just to keep it in more reasonable ranges. So usually you won't see z-scores less than -3 and less than -4. You can just look at the graph. When you get a z-score over 3 or less than -3, you have very, very small probabilities. Okay, so we don't look at those usually very often. Let's just have a slider here. So what we're calculating from any z-score, so right now when z equals 1, if you look on your table as well, you'll get the same result. When z equals 1 on the table, it will show this value here, 0.8413. And what that refers to is the area under the curve, all the way down to negative infinity, all the way up to 1. So no, this is just like you might get a hint from this way it's described here, cumulative probability. This is a cumulative probability. In other words, it's summing up all the probabilities below, that x is below 1 standard deviation from the mean. Okay, so let's go back to the original problem. I've cleaned it out so that, because we're gonna do it now using z-scores. So the first thing we'd want to do is we'd want to find the z-score for -3 and 4.4. So let's do that. We're going to use this little formula here, x minus the mean over the standard deviation. And I'm going to do it for 3.7 and 4.4. So we'll get, for 3.7, we do, the mean is 4.1 over 0.6 equals negative 0.4 over 0.6, and you get negative 2/3. So just no, this is a benchmark. So 2/3, negative 2/3 on the normal curve always corresponds with 25%. So negative 2/3 is going to be 25% down here. So all of this adds up to be a quarter of the whole area under the curve. And likewise on the other, because there's a lot of symmetry here. So when it's 2/3, 25% is this way. And also when you're calculating a z-score, you're always calculating to the left side. So the probability of it being less than 2/3 z-score is going to be 75 total. But the value we have is here. And let's look at that. You don't need to memorize that. It is a nice little shortcut, but let's verify it here. So if I put my z-score down to negative 6.7, okay, I got, as you notice, it's about 25%. Okay, so we have our first z-score. Let's also do the z-score for, let's come back here for the upper bound. So we do 4 minus 4 over 4.1 over 0.6. Okay, and we get a nice round 1/2. Okay, and so let's go to 0.5. Okay, so a z-score of 0.5. And notice I'm doing the same thing you could do by looking up a table. You could look up at the table. If you look up the table for z equals 0.5, you should see this value here, 0.691. They probably rounded up to 0.5 or 69.15. We'll just round it to 69. All right, so let's look at this in probability notation. So the probability that, this is what we're looking for, 3.7 is that x is between this value and this value. Okay, so when we're using z-scores, what we're going to do here is we're going to change this into taking the upper bound, the probability that it's less than the upper bound, and we're going to subtract the probability that x is less than the lower bound. Now these are the areas that I just calculated. So let's refresh our memory here. This one was about 69% for when z is 0.5, or in this case the z-score is for 4.4. So this is about 0.69. And this other value we calculated, the z-score was 0.25. Okay, so we subtract those and we get the same answer we had before. Okay, that's good. Okay, looks like more work for the z-score, and I guess it is technically, but if you don't, the good thing about a z-score is you don't have to keep plugging in different means and different standard deviations. All you have to do is calculate, rescale everything to a z-score, And it can be done pretty quickly because this is a very simple formula. And you have to be familiar with this formula anyways for some more complicated problems that we'll see.